Hello everyone, this is the video lecture of section 1.4, first part out of 2 parts of Math 4500 partial differential equation. Okay, here we're going to learn about first order linear PD with 2 variables. Okay, so first of all, here we're going to use u for the unknown function of 2 variables, We're going to use for now x and y. Independent variables are x and y. U is the name of the solution function we are looking for, satisfying the given PD. So let's begin with some basic ones. Example 1, A. Now y partial of u equals 0, identically 0. Even though u is a function of 2 variables, x and y partial is 0. That means, what does it mean? That means u is independent of y. So it should not have any term which includes y. Alright? So that means u of xy must be a function of x only. Okay? For arbitrary C1 function f. C1 means continuously differentiable. Okay? So y partial of 2 variable function equals 0 actually means that this is 1 variable function of x. Okay? So B. What if you have u sub y equals f of x? Okay? So if you have a 1 variable function f prime of x equals k, then your f of x must be kx plus another constant, right? Y partial is f of x. With respect to y, f of x works like a constant, right? That means u of xy, just like this. This one times this variable y plus another constant, another function of g of x. So when you take y partial, we treat g of x as just like a constant. So y partial of this one is 0, just like a constant. Y partial of this one would be just f of x, right? Similar to this. So y partial of y equals function of x. That means u of xy must be that f of x times y plus another function of g. Okay? For arbitrary g. ARB stands for arbitrary function g of x. Now, C. What if u sub y equals 0? Okay? Now you have to realize that this is u sub y of y partial equals 0. Right? Then we saw that y partial of something equals 0 means that that something is a function of x only. So that something is u sub y. Instead of u, we put u sub y. So this one, inside something's y partial 0, that something must be a function of x for arbitrary function f. Okay? And then we learned that when y sub y equals f of x, that means u of xy must be f of xy plus g of x. Okay? So these are very special case, easy case. Alright? Now, before we move on to the next level of example, let's recall what you learned in ODE. When you have this, you can consider this as linear PD or separation, a separable equation. So anyway, this is the exponential model, right? So then you get y equals some constant c times e to the negative 2x, right? Now, if you have a y double prime plus 9, y equals 0. Linear, second order ODE, then what do you do? You consider characteristic equation. R should be plus minus 3i. So you come from e to the rx. When you have e to the 3ix, that would be cosine 3x sine 3x. So this one will be c1 cosine of 3x, another constant c2 sine of 3x. Okay, using characteristic equation. All right. So because of this, example 2, a u sub x plus 2u equals 0. So u is supposed to be a function of x and y, but x partial. So we consider y is just like a constant. Function of y is a constant. So from this, u of x, y must be, your constant will be some function of y, right? F of y. Any function of y times e to the minus 2x, right? For x partial derivative, function of y will act like a constant. So this will be solution. Okay? Where f is an arbitrary function. Okay? Now, likewise, if you have u sub xx plus 9u equals 0. Again, we only consider x partial derivative. Function of y will be considered constant. So instead of c1 and c2 constant, function of y, function of y. Okay? So u of xy will be f of y cosine of 3x and g of y sine of 3x. Okay? Here, f and g are arbitrary functions. Okay? So far it is almost ODE level, right? Or calculus 2 level. Next up, example 3. Solve u sub y x equals 0. So, if you have u sub xx equals 0, you could have, instead of x, you switch the role of xy, right? Now, what if it is mixed? X partial derivative of y partial derivative of u equals 0. So, by writing solution, by writing this one as u sub y sub x equals 0, what can you say? It's a constant with respect to x instead of y. Then that means u sub y of xy equals function of y. Okay? Where g is arbitrary function, an arbitrary function. Now, unlike this one, y partial with x function, y partial y. So you can't consider this as constant. That means u of xy should be y antiderivative of g of y. Okay? G of y dy. Okay? Because when you take y partial derivative of this, you're going to get g of y. Here, I just leave this one open. It can be any constant or arbitrary constant. That will be just give you arbitrary constant. Any antiderivative of g of y. That's what it means. Plus constant. Here, function of x. I'm going to call it f of x. Right? Arbitrary f. Arbitrary function. Right? Arbitrary function of x, when you take y partial derivative, it's going to be 0. So I'm going to call it capital G of y plus where f and basically g of y is arbitrary function here, right? Antiderivative of the arbitrary function will be also another arbitrary function. So I can just say that are arbitrary functions. So the solution for this will be sum of function of x only plus function of y only. That's the only form which could satisfy this second order partial derivative, partial differential equation. So these are the special cases which do not need any kind of theoretical development to get the solution of. All right. Now next, I'm going to call it the constant coefficients. Okay. So first order linear PDE of two variables with constant coefficients. Okay, so like this, constant times u sub x plus constant times u sub y equals, say, 0. Homogeneous, linear, first order linear, Li stands for linear, partial differential equation of two variables with constant coefficients. So I'm going to call it equation 1. Okay. Now, we need to go over, recall, to understand this one well. Think about directional derivative. Do you remember? Directional derivative of f of xy in the direction of a vector AB. Okay? Or we can write it A I hat B J hat. This is 1, 0 vector, 0, 1 vector. Now, this is called, we use this notation, right? So it's the rate of change of a function for a given point, right? Given xy. Let's say this is vector v. Then this directional derivative is rate of change of this function f in the direction of v. When you go in the direction of v, how much this function will changes per unit distance in the direction of v. All right. And then we learn so v f at xy. So you can write it this way. H going to 0, f of point xy plus h times v. So over this one minus f of xy over h. Okay? Now this one can be written as h going to 0, f of x plus ha, right? hb, right? B equals ab. ahy plus bh minus f of xy over h. Normally, we use this restriction. V has to be a unit vector. Then this will be h unit distance away from xy, right? So if v is unit vector, by h times v will make it in that direction very-ish. H is supposed to be a small number, right? This will be hv. So between xy and xy plus hv, this is h unit distance away from xy in the direction of v. So you calculate the function value over here and over here, subtract, divided by the distance between those 2 points. Okay? Because v is a unit vector, h times v will be size h. So the change of function value per unit distance, that would be directional derivative. And then in calculus 3, we found that there is nothing but gradient of f at a xy times dot product with v. So that means round f round x times a, round f round y times b. Okay? I'm going to write it as a times f sub x plus b times f sub y. So that would be your directional derivative. Okay, knowing this, let's take a look at this one again. A u of sub x, b times u sub y. A, instead of f, you have u. That is just directional derivative of function u of xy in the direction of v, where v is ab. Now, even though original directional derivative concept required v to be 1, but v can be any vector. It doesn't have to be unit vector. All right? Still, everything works. It's just that your interpretation has to be changed. So if your v is a size 10, then this value is not going to be rate of change of the function in the direction of v, because when you have h dividing by h, if it is 10, you should have had 10 times h to measure the distance between the points, right? You're divided by h. So this is, if you put 10 and 10 over here, then it is rate of change of the function per unit distance times 10. So this will be directional derivative of, in calculus 3 sense, times size of v. Okay, negative v. But at least this one works, all right? The physical interpretation will be different, just constant multiple. So this is directional derivative as we know of in the direction of v times magnitude of v. This value represents. Okay? Anyway, this one. So when we consider vector v out of this quotient a and b, then number 1 PDE is same as our unknown function's directional derivative with respect to v equals 0. Okay? So what does it mean? This means some derivative is constant means derivative is 0 means it is constant along that direction, right? So u is constant. C-O-N-S-T means constant. In the direction of the vector v. Okay, which means u is constant on the line parallel to v. Okay, so now think about it. Let's say your velocity vector, no, not velocity, I'm sorry, direction vector v is in that direction. So all the lines here, this parallel direction, you have the same constant. Your unknown function will be constant along these lines. Along these lines. Okay? So this means that u is constant on the line. So this is b over a, slope b over a, right? So y equals b over ax plus some constant. I can rewrite it as c1, ay equals bx c2, ac1 constant. This is arbitrary constant, right? Slope b over a. You can rewrite as bx minus ay equals minus c. So I'm going to call it just arbitrary. Different k value, different y-intercept, but all of them have the same slope, b over a. Slope comes from direction vector v. So u is constant on the line. Bx minus ay equals any constant. Okay, any constant. All right. And note that vector AB dot product with B minus A, AB minus AB equals 0, perpendicular vector, right? So this is another way of writing your line equation whose normal vector is B minus, right? Just like a plane equation, you can use this. Normal vector dot product with x and y equal constant. But anyway, either you get it this way, elementary pre-calculus level, or using the parallel arguments as derivation of plane equation, same thing. Anyway, so I could write it this one as c equals, let's say, c equals -1, c equals 0, c equals 1, c equals 2, c equals 3, you know, different c values and different, let's say, these are the cases, right? So, again, this equation, solution of this linear, first order linear PD with constant coefficients has to be constant on the line, this kind of line, okay? From there, we can derive first major theorem, okay? Let me write it here. Oops. I don't understand. Okay. So, theorem 1. The PDE number 1, that one, has a solution xy equals some function of bx minus ay, where f is an arbitrary C1 function. Again, one is differentiable once, and that derivative is continuous. C for continuous. So C1 means continuously differential. So, here, what we found was that on a given line, bx minus ay equals k, the solution is constant. Solution u is constant. U has a constant value. Obviously, different line, you have a different value. So different k value will give you different lines. So let's say, I'm going to call it k here, right? Then these are, let's say that k equals k. K equals maybe 1, 0, 1, 2, 3. Then, all the points on this line, your solution will have the same value along this line. But on this line, also possibly another value, right? So, your solution function depends on this k value. So, if you give me any point xy, then I can find k value k value for which this line includes the given xy, right? So, depending on k, right? So, our function, this is a function of k value corresponding to given xy. So for this xy, corresponding k value equals 0. For this xy, corresponding k value equals 1. For this xy, corresponding k value equals 3. For this xy, maybe corresponding k value will be maybe 1.5, right? So, because our solution have the same value along all such lines, it just depends on what line you belong to, which means what k value you belong to. So your solution function, solution's value will be depending on these k values, depending on the lines you're belonging to. That means depending on k value. So it's a function of k. Now, what is that k value? For given xy, by doing this, bx minus ay will give you that corresponding k value. So, that's how you get this, alright? So, f can be some function here, any C1 function, right? So, our solution will be f of bx minus y, ab, so xy in the order, ab, then bx minus ay, any function of that, alright? It could be sine of bx minus ay, or e to the bx minus ay, some function of one variable. That variable is replaced with bx minus ay. Then it will give you the solution. Okay? So this is the first major theorem for this first order linear PDE with constant coefficients of two variables. Now before we continue, let me check the recording. Let's do example corresponding. This was proof. So example 3. Solve the following PDE with a boundary condition. Okay? BDRY stands for boundary. Again, BDRY stands for boundary. Condi stands for condition. So with a boundary condition like this. And u of x0 equals x cubed. So your function, your solution function u, unknown function u of xy, defined on an xy plane. Our so-called boundary is when y equals 0, here on this line. So it will be x0. So on that line, your solution value will be following x cubed. So if you have a 2, 0 at that point, your solution function has a 2 to the third, 8, right? So we want to solve this kind of boundary value problem of PDE. All right, the solution. According to this theorem, this is A and B. Our solution has to be some function of bx minus ay, b minus bx minus ay for y, for some function. Now, for this differential equation, it can be any function, any C1 function. Now, we have to find such function for which this boundary condition is also satisfied. So that's why I say for some function to be determined. To be determined, right? So let's use this. X cubed u of x0. Now, from this x is 0, that means f of negative 3x, right? So now I have to find f of function f. So I have to write an f of something equals f of z equals z something, right? So I'm going to set z to denote minus 3x. That means x equals negative 1/3 z. So plug it in. Negative z over 3 cubed equals f of z. Therefore, f of z equals negative 1/27 times z to the third power. So here that function f is this. All right. Therefore, our solution u of xy is f of negative x negative y, f of this, which means minus 1/27 times, instead of z you have minus 3x minus 4y to the third power. If I take minus out, negative 1 to the third power negative, negative cancel, so you can write it 3x plus 4y to the third power over 27. So that would be our solution to this problem. Okay? So here, you can check. All right. What is 4 u sub x minus 3 u sub y? Okay? So u sub x, in order to take x partial, what do you do? 4. Something to the third power, you have to do chain rule. X partial of this one is 3 times this one to square. 3/27 is 1/9. Whatever the inside, the second part, times derivative inside. X partial derivative inside, which is 3. Okay? Chain rule. Minus 3 times, now y partial of this. Again, using chain rule, derivative of outside function, 3 times this thing, 2 squared, 3 cancel, so 1 over 9, whatever the inside, second power, times y partial derivative inside, which is 4. So what do you see? These are equal. 12 over 9, 12 over 9, same thing. As we expected. Indeed, this one satisfies this. Moreover, if you put x 0, u of x is 0, what is it? 3x 0 to the third power over 27. Yeah, that is 27x cubed over 27. Indeed, it becomes x cubed. Okay? All right. Okay. So that would be the end of the first part of section 1.4. All right. There will be a second part. So we'll see you next time. Okay. Bye.